Here we go, guys. So the topic for what we're doing today is stoichiometry. And what I need you guys to do, please, is open your books to chapter 3. That is page 77. And again, if you guys are good. You need at least a book between you. So if you don't have one per, we'll be okay. Yeah, that's fine. We're just going to need, and frankly, I can probably feed you most of the masses that we need just because I know them. But we are going to need some masses to do some calculations. So, guys, here's the scoop. Well, maybe we should talk about a couple of things before we get going. Guys, following Tuesday's time together, especially in this class, I had several people come up to me and express concern. One about whether they should be in this class based upon their academic chops or their plans for their life. But frankly, a couple of you came to me and said, frankly, I'm looking beyond this into college, and the reality of it is that while I do need good experiences, and I know this class will prepare me for college, the bottom line is money's important to me as well, and I'm afraid I'm going to blow my 4.0 because of what you said about grades in this class. Okay, guys, we need to talk about this, and I know that I can't. You just have to trust me. Guys, I can't show you my grade books from previous years, but if I could show you my grade books quarter by quarter from previous years, you would see a string of A's. 90% of my students every quarter get an A in this class. And the kids that don't get A's, if you go and ask them why, they can tell you why they didn't get A's, and it has absolutely nothing to do with their abilities in this class. It's because they're being idiots. So, guys, please don't let protecting your GPA be a motivation in here. Do you remember when we drew the two curves on the board? And we talked about the idea that you guys are the best and the brightest in the school, but I need to give you feedback relative to the way the AP test is graded. Guys, understand that your grade is not based on your test scores. Your test scores are going to be realistic based upon a population of 100,000 AP students around the world. But that's not what your grade is based on. We rewrite tests, we do chapter summaries, you guys do the things you're supposed to do, and you just got to trust me. I'm not out to stick you, and the structures that we have will honor the fact that you guys are the best and brightest, because GPA is only a comparison to the people in this school. And I honor that. It doesn't mean you're guaranteed an A, but you're actually going to have to really fumble the ball in order to not get an A. Okay? So, with that said, guys, please don't let that play into your thinking. The other thing I would mention is this, and if you need to talk to Nathan's mom about this, I would really encourage you to do. You know, she runs our career center. Guys, she is probably going to become one of the most valuable people in your life if you're a senior. Because, guys, money is king when it comes to going to college, and she's a genius at finding scholarships for you. Go talk with Nathan's mom like yesterday and get started with this. But the other thing you're going to find, guys, I was talking with her the other day. Do you know that universities are radically changing their admission requirements? Yeah, what is it, Southern Utah? Down in Cedar City. They actually now have changed their admission and scholarship rubrics. So it's now not GPA and ACT, it's GPA or ACT. So guys, admission and scholarships is no longer that weird matrix where you just have to be in that upper left-hand corner. It is now an or rather than an and. So guys, again, with this theme that the reality is what's going on in the moment. Guys, things are changing. So you need to start asking these questions. So, can we go on? Are you guys, you're good from Tuesday? You're not going to drop the class. You're not depressed. You don't need a hug. None of that stuff, right? We're all good? Okay. So, Guys, the reason that I say all of that is because after today, we may have to have another group hug because some of you are going to feel beat up after today. So let's talk. So guys, look at the title of chapter 3. Stoichiometry. When did we do this in general chemistry last year? Right before quarantine, right? So guys, this was one of the last and hardest things that we did. And it turns out that because this is a college course, it's the 3rd chapter. And the first chapter is, let's make people love chemistry. So before that's a little bit about measurement, and then we jump right into stoichiometry. So guys, I say that to say this. Page through this with me. Ready? Page 78. A glorious picture of Anton Lavoisier. And then we start talking about chemical equations, reactants and products. Then, guys, balancing chemical equations. Familiar, right? Then we turn the page again and we move on to page 81. And it talks about indicating the states of reactants and products, solid, liquid, gas. And then if it's dissolved in water, it is soluble. But what's the subscript we put on? Do you remember? AQ for aqueous. Do you remember that maybe a little bit? Okay. Then, guys, we go on from there. At the bottom of page 81, it talks about patterns of reactivities. That's all about reaction types. Single displacement, double displacement. Sounds a little familiar from last year? Okay. So you'll notice that they don't call them that. On 82, they talk about, we called them synthesis and decomposition. This calls it combination and decomposition. That's fine, just different words. Then down at the bottom in 83, it talks about combustion reactions. Then turning the page again, we start getting into formula weights. And we figure out the weights of things by adding up the weights of the parts, and those numbers are in AMUs. Remember that? Okay. Then, guys, at the bottom of page 85, this is a little new. We'll talk more in a minute. Then, guys, turning over to page 86, the magic of Avogadro's number. This is a lot of material for 7 pages in the book, right? This is what college feels like. Okay, so then, guys, we got the mole on page 83, 86, moving on to 88. We've got molar masses. The idea with molar masses is now all of a sudden the numbers aren't in AMUs, they're in grams, because we're talking about moles of things rather than individual things. That would be page 88. Then, guys, we go over to page 90. And it's all of these mass to moles problems. This was actually the very last thing that we did before quarantine struck. That takes us through 91. Then, guys, we get over to calculating empirical formulas on page 92. Then we get into page 94, and we didn't do this last year. Molecular masses from empirical formulas. We'll pause on that for a minute. Then, guys, we go over to page 96, and this is where it really starts to talk about stoichiometry, where the number of molecules go in has got to equal the number of molecules that go out. If you turn the page again to page 99, do you remember limiting reactants? What makes something a limiting reactant? It's the thing that you run out of first, right? You remember my stupid bicycle analogy, and we ran out of wheels first, remember? It was stupid to you, but meaningful to me. Then, guys, we turn over again, and that takes us back to page 102. You may remember the lab that we did where we calculated theoretical yields. We'll talk more about that in a minute. And then, holy smokes, the chapter's over. So, guys, now you're saying to yourself, if this is what this class is going to feel like, this is going to be crazy. Guys, we will never do this again. We will never allow the book to drive instruction. We will never reference the book during instruction ever again unless we simply go to page 500 because there's a picture there we need to look at. But guys, today we are actually going to cover all of chapter 3 in one class period. The reason that we're doing this is because this is all review with a couple exceptions. Now, guys, understand, I know you're at a little bit of a disadvantage because it has been 5 months rather than 3 months since you were engaged in this material and you didn't do summer homework. So, guys, if this feels a little bit overwhelming, give yourself time. We'll be moving into these ideas as we go. But, guys, we are going to run through chapter 3 today. If we run into stuff and you're like, okay, I just need to talk about that more, please slow me down. There are places where I will slow us down because there's new information. We'll be doing some problem solving and stuff like that. Then, guys, the last thing I want to point out to you is this. Look at page 105. Go there with me. All of your homework in this class will be out of the book. I will never hand you worksheets in this class. So when you see the homework assignment, they are always the end of chapter problems. With that said, guys, notice that the very first thing you see on page 105 is visualizing concepts. And there, that page 105, you'll notice there's a lot of diagrams and a lot of drawings. Guys, these are visualization questions that cover the entire chapter. These are important because in this class you're going to be drawing a lot of pictures, especially on the tests. With that said, turn the page again. And then starting on page 106, these questions become more mathematical and they actually range through the chapter. So starting on page 106, section 3.1, there's some questions. Down at the bottom, 3.2, there are some questions, and you'll notice it just goes on page after page after page. So guys, that's where your homework will come from. We will be doing the visualizing questions as well. You get the idea? All right. So guys, with that said, slow me down if and when you need, and we're just going to skip through these things progressively. Go back to page 77, and here we go. And again, guys, if you're going, man, this is not what this class is supposed to feel like, it will never feel like this again. We're just doing this now. Yeah. Oh, yeah, absolutely. But no, well, good question. So what you're going to find is that guys, you probably didn't hear Matthew's question. He said, if we have notes from last year, will that cut it? And so what you're going to find in this class is there's very little that we'll talk about in here that we didn't talk about last year, but at a much different level. So if you're suggesting, should I maybe not take notes? Remember, I post all my notes online if you want to print them. But the other thing that you're going to see is when we're done at the end of chapter 3, which is going to take us an hour, we will have covered 2.5 months of material from general chemistry. Right? I mean, think about how we rolled it. Like, we did Avogadro. I mean, it's just, this is months of stuff in Gen Chem crammed into a chapter. So I think it would be hard to find, hey, this set of notes from Gen Chem covers this. You know what I'm saying? So if nothing else, Matthew, just from knowing you and working with you, I think the thing that you may want to do is at least write down the problem solving. And so maybe there are things, and this is to all of you, as we're going through this, maybe you're like, oh, that's something I should remember. Scratch that down, and then maybe write down the problem solving. So, yeah. And guys, that's a skill that you're going to develop in this class, is the ability to take notes. Guys, in college, you've got to learn this. Don't take dictations, take notes. Never just blindly write down the stuff on the board unless it really seems necessary. What you want to be doing is jotting down thoughts and ideas and reminders, because if you're going to try to write everything down, you're going to explode. Don't try to do that. So, guys, starting in 3.1, balancing equations. Is there anything that you want to talk about relative to balancing equations, or do you feel somewhat comfortable with it? Thoughts or concern? Do you guys remember the tricks to balancing equations? Should we go over would it be helpful to at least go over the tricks and see if they're... So the tricks that I shared with you last year were things like this. First of all, and don't try to write this down, just think about it, balance polyatomics intact if you can. Do you remember that idea? So the idea was that if we're balancing an equation that was like the precipitation reaction when lead 2 nitrate reacts with potassium iodide, and out the back side of that we get potassium nitrate and then lead 2 iodide. If we do something like that, then guys, when we balance this thing, we need to balance the leads, but do we need to balance the nitrogens? No, why not? because we can balance a nitrate here and we can balance a nitrate there, and consequently we don't need to balance the nitrogens, we can balance the nitrates because these polyatomics stay together and therefore we don't need to balance them. Is that coming back to you? So an example of the opposite would be something like this. The decomposition of potassium, sorry, that's a 2. The decomposition of potassium nitrate into nitrite actually looks like this. And in this case, we cannot balance the nitrates because here we have NO3 and there we have NO2, and those aren't the same, so we can't balance them that way. Do you remember that idea? Okay. And this actually brings up another interesting thing that we need to talk about. Guys, and this was another trick I shared with you last year. Guys, if we tried to balance this equation, we would find quickly that we're stuck. The reason that we're stuck is because we have 3 oxygens over here and we have 4 oxygens over here. Do you remember that concept? We have an odd-even conflict. Remember that idea? So guys, what do we do to resolve an odd-even conflict? Double the odd number, making it even, and then it balances. So if this is our odd number, we'll put a 2 there, and then go back and rebalance it, and actually it just does this, and then it balances. But guys, if you get in that position where you've got an odd and an even number of atoms, double the odd number, make it even, and start over. Is that coming back to you? Okay. Other tricks that I shared with you last year, balance oxygens last. You're going to find out that there's oxygens just spread all throughout these reactions. Balance those last. And then finally, guys, if you really get stuck, just strong arm these things. Throw a 2 in front of the very first thing. See if you can get it to balance. If that doesn't work, get rid of the 2. Put a 3. See if you can get it to balance. And eventually you'll get them to work out. So, guys, with that said, things that you need to talk about relative to balancing equations. You guys okay? Please ask if you need. You're okay? Okay. So, guys, with that said then, section number 2 is actually all about patterns of reactivity. Potassium. Yep. So, guys, moving through into patterns of reactivity, this is all about reaction types. You want to go over the 5 types just to remind ourselves? Okay, scratch them down. This is probably worth writing down. The first one is single displacement. So guys, in a single displacement reaction, you have some element A reacting with some compound B, C. And when that happens, A will either hook up with B or with C. How do we know which one it'll hook up with? Go ahead. Beautiful. Yeah. So the one with the opposite charge, but how do we know the charges of B and C? Always. Well, in a salt, it always goes first. In a molecule, it can change. But in a salt, yes. So, guys, B is always positive. C is always negative if it's a salt. And then A will hook up with C if it's positive, and A will hook up with B if it's negative. So let's say in this example that A is negative. Write the products of this reaction. If A is negative, what's it going to make? So guys, if A is negative, who does it hook up with? So why is your product not AB? Positive first. So it's BA, and then C gets the bootski. So guys, that would be single displacement. Then let's come back and let's look at double displacement. So this would be AB plus CD. Please write the products. So, guys, as you're writing this down, I think I just made an executive decision. Again, as I was talking with Nathan a minute ago, and we were talking about this idea that normal is whatever's going on right now, because tomorrow's probably going to be different. I'm realizing, just from interacting with you guys a little bit, that they're collectively, it's just been a long time, right? I mean, normally in this day, we're half done because my students have done all the summer homework. All of this is really fresh in their memories. And this is not an indictment of you guys at all. You just didn't have that opportunity. You've been disconnected from this stuff. Guys, I think what we're going to do is we're just going to slow down. I think that the best thing that we could do right now is rather than try to rush through all this material in one day, let's slow down, let's regroup, let's give ourselves a couple days to reconnect. So what I'm going to do is actually, and we'll see how this goes. This may not be 2 days of material, but I know given your guys' lack of exposure to this material, it's not going to do you good for us to rush through this in a day. Normally it's appropriate, but now it doesn't make sense. So guys, we're going to slow down. Let's really allow ourselves to chew on some of these ideas and really re-engage with them a little bit. So you'll see. We'll just stop when time runs out, and we'll pick up wherever we get on Monday, and we'll go from there. Okay, all right. So guys, with that said, predict your products. This will be nice because now we don't have to rush. So guys, given the information that you have on the board, you should be able to figure out the products. As you're doing that, allow me to whisper in your ear. Guys, one of the skills that you need to develop in this class is the ability to overcome the thing that goes through your mind that says, oh crap. Because when you sit down to the AP test, every single question on that test, the first time you read it, the first thing that's going to go through your head is going to be, oh crap. And guys, if you haven't developed coping mechanisms for oh crap, it could describe your performance on the test. So, guys, what you want to do is you want to start to develop different reflexes. So if I ask you, please write down the products for this reaction, and your first thought is, oh crap, the most important thing you're going to do is what you do next. And so, guys, for some of you, that might be another sheet of paper and you start just jotting notes to yourself. For some of you, it might be to go back and reread the question. For some of it might be, let's start writing down charges. But, guys, you've got to get over that initial freeze and start doing something. So, the thing that I would do first, even if maybe you didn't need to do this, but I throw charges on things. So if you didn't see it previously, I'll bet you see it now. So guys, what does A hook up with? Yeah. A first, right? Yeah. So A first, and then who's our other guy? CB. Do they have to be in that order? Could the CB come first? Absolutely. That's reflexive, right? But you can't have DA because it's always positive first in terms of charge. Is that okay? Because the rule with naming salts is the metal always goes first. But Spencer, you actually bring up something interesting because we haven't called it that yet. Ronnie mentioned the idea that the positive one goes first, but it's neat that you remember that that's the metal. The metals are the positive charges in these salts. So you're absolutely right. Go ahead. Oh, sorry, just a second. Go ahead. What? They can, but then they don't form salts, they form molecules, and it's only the metalloids. Remember the ones on the stair step? Those actually can become negative, but then they form molecules and not salts. And we're going to talk more about that later. I got you. Go ahead. Yes. Yeah, that's a really... do you feel it starting to flow a little bit? The blockages are starting to loosen up? That's a great question. So how do we pick charges? And let's make that question even harder. Did you guys catch the question? Pointing at the periodic table, how do we know which charges to use? And it gets even worse because how do we know which charges to use if we don't have any charges, right? And so the answer to the question is, you'll always know by context. So let me show you what I'm talking about. So for example, this. Let's just draw our, let's do this. So this guy right here, okay, PbNO32. So PbNO3 2. What's the charge? Pb is lead. What's the charge of lead? It could be +2 or +4, but it's got to be one or the other. Which one is it? It's +2. Now the question is, how do I know? And the answer is context. So what's the context? Well, the context is that nitrate is -1. So then the question is, how do you know that nitrate's -1? Because it's one of them that you need to memorize. Do you now see the necessity of that memorization? Because, guys, if you know that nitrate is -1, you now know that this is -2, and you now know that this is +2, and it gives you that charge. And so that's one of the major reasons that we're memorizing the names, formulas, and charges of those polyatomics, because many times it's the back door into figuring out the charges of the other guys. So once we have that, we can then come back here and we can go, okay, if lead is +2 here, it's also going to be +2 here. Iodine's -1, so now I need 2 of them. And then the pieces start to fit together. But again, it all comes back to knowing the charge of nitrate. So on the first test that we take, I will probably let you use the ion chart simply because you haven't memorized. Well, you'll be close to memorizing them, but not all the way there. Just a second, Spencer. Are you okay? So, Spencer, that's a good question. Why does lead have to be the same? And the answer is it doesn't. And when we get into chapter 4, we're going to start looking at reactions where the charge changes. But again, there's going to have to be evidence that leads us to that idea. So, guys, let's do this. Good. Single and double displacement. You feeling okay? Okay, so, and guys, again, when you learned these last year, we talked about the idea that these are sort of similar conceptually. They're displacement reactions. So now let's do this. Synthesis and decomposition. These are related processes as well. But the book uses a different name for one of them. Combination. So not synthesis, but combination. Either term is fine. But guys, let's talk about what these mean. So a synthesis reaction simply takes pieces and puts them together. So what about decomposition? Yeah, they decompose. It takes them apart. Now, guys, if you remember last year, which most of you don't, I protected you from the decomposition reactions. Even when we did these in homework, I told you the products of the decomposition reactions. That will not be the case this year. You will actually be held responsible for figuring out what things decompose into. So how do you know? Well, one, we're going to do them in lab, and you're going to collect the products and identify them. But there are also some tricks that we can teach you along the way that'll help you as well. But these are synthesis and decomposition. Again, if you need the anchors, remember synthesis, one product, decomposition, one reactant. Good? Okay, one more. Combustion. So guys, last year we said that a combustion reaction was simply this: a hydrocarbon burning in the presence of oxygen to produce carbon dioxide and water. It's the weirdest thing, right? How do you get food in? No, don't do that. You're just fine, but yeah. So drinking coffee is even worse, and by the middle of the day, I get this little coffee stain in my mouth. It's really gross. Sorry, I shouldn't have showed you that. Guys, remember combustion? What do they always include? They always include a reaction with oxygen. Your products are always carbon dioxide and water. With that said, this is actually not the complete definition of a combustion reaction. Because combustion reactions, and I'm going to write this over here so that you can see it. Combustion reactions can also involve the burning of alcohols. For those of you that don't know, an alcohol is just a hydrocarbon with an OH attached to it. And those things also combust. They also form carbon dioxide and water. The equations balance a little bit differently, but those also combust as well. No, so there's lots of other things that combust, right? Like, for example, cellulose, wood, also combusts. And actually, cellulose is largely carbon, hydrogen, and oxygen. But the way those things combust, the products are more complicated than carbon dioxide and water. So that's really the thing that we're looking for, is things that burn oxygen to make this. And it's not completely exhaustive, but it's good enough for us. Yeah? So let's talk about it. So the word we're looking for is exothermic. They are always exothermic reactions. They always give off energy in the form of heat and light, but absolutely. Yep. What's that? No, so let's do this. This is always exothermic. You know what? Let's leave it at that right now, Nathan, because frankly, so the thing that we can say for sure is this: forming bonds always gives off energy. Breaking bonds always takes in energy. So then from that we would say, well, if forming bonds always releases energy, shouldn't this always be exothermic? And the answer is not always. And we're going to talk about that in the next unit. So I don't want to draw any lines in the sand that we have to fix later. So we can just say this is always exothermic. Are you guys beginning to get a sense of why it's so hard for me to teach general chemistry? Guys, there's 11,000 things that we talk about in general chemistry that I can't even talk about. Right? And all of a sudden we're having all these wacky conversations about stuff, and you're like, oh my goodness. Yeah, general chemistry is so protected and locked down, and it's all out there now, so we're doing it. So are we good on the 5 reaction types? You guys good? You're going to find that there are other reaction types we'll talk about through the year. We'll talk about redox reactions, acid-base reactions, gas-forming reactions in Chapter 4. But for now, this is just review, so this is what you need to know. All right, so can we go on? We good? Okay, so this, I think, is going to bring up the reaction types. Okay, so now let's get into atomic weight. And I need to be careful because this actually jumps. Okay, so, well, here, let's just talk about it. So, guys, when we talk about the atomic weights, we're talking about these masses or weights on the periodic table. So, guys, on the periodic table, what are the units for these masses? I'm going to call them masses instead of weights. What are the units? They're in AMUs. And reminding yourselves, what is an AMU? The mass of, say it again, atomic mass unit, but what is it fundamentally the mass of? A proton or a neutron. Within 4 significant digits, they weigh the same. And so, guys, these masses are all masses of one atom in AMUs. But the trick is for example, if we've got a carbon atom, so carbon and then the electrons like so. And so electrons, what's the mass of an electron in AMUs? Functionally 0. It's actually an 1800th of an AMU, but we round it to 0. So, guys, this nuclei weighs 12 AMUs. But if we go and look at a carbon out, if we look at the mass of carbon in the periodic table, the mass is listed as 12.0107. What's going on? Go ahead, Matt. Averages of what? Not ions, different isotopes. So, guys, for example, can I borrow this? I want to make sure I don't know if my eyes can do this anymore. Guys, you guys have young eyes. I don't. Go up here to the very tippy top. Did you guys ever know this is here? the masses of the decays of the isotopes? Can you guys read that where it says selected isotopes? How many isotopes are listed for carbon? It should be 3. Okay, it is? You only see 2? 11 and okay, so I'm pretty sure there's 3. Anyway, we can talk. So I really think I'm right about this. So you've got, wait, it just says 11 and 14. Oh, they missed 12. So guys, I believe that this is the exhaustive list, that carbon actually exists as 3 potential isotopes. So if you get a chunk of graphite out of your pencil, you know that that's actually carbon and not lead. Maybe you know that graphite actually looks like this. That graphite actually forms in sheets that we call graphene. The sheets are held together, the atoms are held together with covalent bonds. The sheets are held together with intermolecular forces, which is what makes graphite very brittle. When you break your pencil lead, it's carbon. When you break it, what you're actually doing is shearing the sheets of graphene off of each other. It's pretty cool chemistry. But, so guys, if this is what graphite looks like, each one of these black dudes is carbon, and they're all carbon, so what do they all have in common? What do all carbon atoms have in common? 6 protons. If it ain't 6 protons, it's not carbon. But they're also different. So we've got 6 protons, 6 protons, 6 protons, because that makes them all carbon. But guys, the thing that's different is the number of neutrons. So guys, how many neutrons does carbon-11 have? 5. And carbon-12 has 6. And carbon-14, which is radioactive, has 8. And so when we say that carbon has a mass of 12.0107, it's actually the average of all the masses of these isotopes. So if we grab a chunk of pencil carbon and if we separate it into its different isotopes, and if we take a weighted average, we're going to end up with 12.0107. Now guys, in this class, you actually need to know this. How on earth do we separate and count atoms? Did we talk about this last year? It's called mass spectroscopy. And what they actually do, this is brilliant. This is the analogy, and then we'll look at it in a minute. Guys, the way they do it is, imagine that I had a trash can, and the trash can was full of bowling balls and volleyballs. Okay? And imagine that we wanted to find the average mass of these balls, but we don't have a scale. What could we do to figure out the average mass of the balls in the bucket? Throw them. Guys, what you actually do is this. You would get a lever arm that adds the same force to all of these balls, and you would pick one up, set it in the lever. My mask is freaked out. Sorry, guys. Pick up the ball, set it in the lever, and throw it. And then you'd throw it, and then you'd throw it, and then you'd throw it, and then you'd throw it. And by the time you got done throwing all these balls, what would be on the floor? 2 piles, right? If this is just volleyballs and bowling balls, we'd end up with 2 piles. Which ones are going to be right here? Bowling balls. Which ones are going to be back there? Volleyballs. How do we figure out how much the bowling balls weigh if we don't weigh them? How far they flew. If we know the force that goes in, and if we know the distance they travel, we can calculate their mass. Same thing with the volleyballs. So we know the mass of the bowling balls, we know the mass of the volleyballs, then we can count the number of balls in each pile and take a weighted average that would give us the average mass of the balls. You do the exact same thing here, but guys, how do you throw carbon atoms? The answer is you turn them into ions. You actually bombard them with radiation, and it strips electrons, which don't have mass, strips electrons off of the atoms, and if you remove electrons, what's the charge become? Positive. Then you shoot them through a magnetic field, and when they go through the magnetic field throws them because they have a charge, and then we can measure how far they fly, and we can weigh them that way, and then count the number of hits, and that's how we get the average masses. That's not bad. Just a second, Spencer. Hold on, buddy. So, guys, I believe there's a picture of this somewhere in our books, if you can help me find it. No, they're stable enough that they don't come apart. Yeah, and so good question. The way that they do it is they boil it. They actually take the graphite and boil it, turn it into a gas, and now we have individual atoms that we can ionize and then throw. Guys, I'm not seeing it, so let me get you a picture. I thought it was in our books. Spencer, hold on. I'm not tracking with you. So, guys, I'm not going to spend a lot of time with it, but this is literally the way that this works. So what they do is they take, this should say, oh, here's the heater. So the heater vaporizes the sample. They boil it. Then they pass it through these plates. Sometimes they do it with plates. Sometimes they do it with radiation. But in either case, they turn these things into ions, and it says ions accelerated. Then they pass it through a magnetic field, and that magnetic field bends the beams. So guys, which one is going to bend the most, the heaviest or the lightest isotope? The lightest will bend the most. It's kind of like if you've got a bunch of kids running by, and if you shove all the kids, the light ones are going to go flying and the linebackers are barely going to budge. Same thing here. And so then what you can do is you can measure how much they bend, and that gives you the masses, and then you can get a hit count, and that gives you the abundance. And that's how they come up with average masses. You get the idea? All right. So density has nothing to do with this, because density is a function of a population, and this isn't a population, it's individual atoms. Let me stop there. Okay, so guys, are we okay with this idea of atomic weights and why they're not whole numbers? Is that okay? All right. So I'm afraid if I touch my screen, this is going to screw up. But no, we're good. Okay, we're good there. And then the averages. All right. So guys, where are we at now? Oh, the mole. Oh. Could you guys tell how much this meant to me when I taught it to you back in the day? Where are we at? 3 what? 4? Oh, good. Okay. Hold on, Spencer. So, guys, let me... okay. So the idea then goes... Let's go back over this. So, guys, if you remember, I sort of led you last year on a journey that got us to the point where we needed the concept of the mole. If you remember the way we approached this last year, I told you that we were going to do an experiment where we were going to find the weight of sodium chloride, and then we were going to go into lab and we were going to weigh that out. And we said that sodium chloride is 23 and 35.5, which is 58.5. And what are the units for that number? AMUs. And I told you we were going to go into lab and we were going to weigh out 58.5 AMUs of salt. And it was probably one of you guys that said, that's stupid because we can't do that. And then we identified the idea that 58.5 AMUs of salt is actually this much salt, right? And then we went, well, I guess that means our periodic tables are worthless because all these numbers are AMUs and we can't use those numbers, right? So then we went through that ridiculous exercise where we said, okay, if we can't measure 58.5 AMUs because it's too small, how do we fix the problem? And then we agreed on the idea that in order to fix the problems, we need a bigger pile, right? Do you remember this? And then we played this stupid game where we said, okay, if one's not heavy enough, then what if we get 12? And that's a dozen. And a dozen weighs 12 times more, but it's still really small. And then if we get a dozen, which is a gross, yes, that weighs more, but it doesn't weigh enough. And then we finally got to the point where we said, how many do we need in order to weigh them? And what was the answer? A mole. So guys, we said that this is how many things we need in order to be able to weigh them. And then we said that if we have Avogadro's number of salt thingies, they're called formula units, NaCl, that actually weighs 58.5 grams. And we got to the point where we understand that Avogadro's number is exactly the number of things that we need to have the group weigh the same in grams as an individual weighs in AMUs. How about that for a quick review? Is that coming back to you? Okay, so now, guys, we asked the question, what are the units on the periodic table? And you kind of hesitated to say AMUs. I hope that the hesitation was because you were thinking, wait, isn't it in grams? So, guys, what resolves that tension? Well, let's come back to carbon. So the idea is if one carbon atom weighs about 12.0107 AMUs, then, guys, Avogadro's number of carbon atoms weighs 12.0107 grams. And it looks like this. Do you remember that? So are we comfortable with the idea of the mole? Do you need to talk about that more? Is that okay? Or AMUs per atom. Exactly. Yep, you got it. All right, so where does that take us? That's the mass mole. And then, guys, that led us to mass mole and particle conversions. I thought that if I stuck my phone underneath my sink, I wouldn't be able to hear it. I've never answered this phone and said to myself, gosh, I'm glad I answered that call. I think we're not going to. Okay. So, hold on a second. So, guys, this then is the thing, and it was a sad day. So, March 13th happened, right? And I came back in August, and our homework assignment answers were pinned to the wall. And actually, guys, the assignment that was pinned to the wall were moles conversion problems. It's kind of crazy. Do you feel like we can approach these? Would you like to look at an example? Since we're slowing down, do you want to look at an example just to get a sense of where we are? Okay, so let's just make something up. That's not good. The chances of that actually being water is closing in on 0. I know. So, the fetus, right, that's in my stockroom. Can we talk about this? Was I the only one that was really kind of like disturbed by that? Oh, you didn't see it? Yeah, there's a human fetus in my stockroom. And so, of course, it belongs to a biology teacher, right? So I started asking the biology teachers, and I walk into Miss Harward's room, Amanda, and I'm like, Amanda, are you missing a fetus? This is being recorded. And she's like, yeah, that's mine. And I said, why is it in my stockroom? She's like, I didn't know where else to put it. So now it's my responsibility to dispose of it, apparently. So anyway, so what if we do this? Okay. Forgive me for a minute. How many milliliters is 4.5 fluid ounces? 133.08. Okay. So guys, this is the question that we're going to answer. What did I say, 133? So 133.08 milliliters Okay. So, guys, they gave us these ridiculous squirt bottles, not of hand sanitizer gel. This is actually ethanol. So this is 70% ethanol, but we're not going to deal with the percentages. Let's pretend that this is pure ethanol, which functionally makes it ever clear. Because do you guys know that the alcohol that's in most hand sanitizers is the same stuff that's in beer and wine and stuff like that? So if it's pure, it's just Everclear. So for argument's sake, let's pretend that this is actually pure ethanol, even though it's 70%. So the question that we're going to figure out is if this, and Siri just told us, right? If this is 133-ish milliliters, oh wait, crap. To do this, we need the density, don't we? Oh, I know the density. That's sad. Okay. So it's 0.79 grams per milliliter. I should give you that information too. How do I know stupid stuff like that? So guys, the question is this. How many molecules of ethanol are in here? You got 2 minutes. Go. And guys, again, if you're having that oh crap moment, you got to overcome it. When you're doing dimensional analysis problems, guys, the best way to overcome the oh crap moment, draw a line. Then figure out your goal. That's pretty safe. What am I solving for? Not moles. How many molecules? Not surprisingly, guys, in an AP class, significant digits matter. Man, this is proving to be a much better question than even I thought it would be at the start. So guys, you got about another 30 seconds. I have no idea. Sounds reasonable. Okay, guys. Let's gather together and let's see if we can plow through this together. Again, guys, the trick here, if you're initially stuck, you've got to be developing strategies that say, when I don't know what to do, here's what I'm going to do. And many, many times, the best thing that you can possibly do is just draw a line. You're now no longer stuck. But then, guys, once you've drawn the line, I would propose the next safest thing to do is pick your goal. And in this case, our goal is simply, how many of these dudes are in that bottle? Well, then, guys, we ask ourselves the next question. What is unique about that bottle that will limit or determine how many molecules are in there? Well, it's not the density, because that density is true whether you've got a drop or an ocean full of this stuff. So the thing that limits the amount or determines the amount of molecules is the volume. So now, guys, we've got to figure out a way to get from the volume to molecules. And eventually we're going to need to get to moles. But what do we have to get to first before we can get to moles? Got to get to grams. And guys, we know that 1 milliliter of this has a mass of 0.79 grams. So now we're magically in grams. 24, 29, 30, 42? No, 46. 46? Okay. So then, guys, we need to know the mass of this substance to get to moles. Carbon is 12, hydrogen is 1, oxygen is 16. Add all of that up, I get 46.0-ish grams. 0.6, so 46.1. So 46.1 grams of CH3CH2OH is 1 mole of CH3CH2OH. But we're not done, because that gets us to moles and we want to go to particles. So what's our conversion? How do we get from moles to particles? Avogadro's number. 1 mole is Avogadro's number. And Spencer, tell me your answer again. 24th. Can anybody confirm or refute 1.4 times 10 to the 24th molecules? Good, good, good. Okay. Guys, notice significant digits. We were limited to 2 significant digits by the density that I gave you. So that would be right to sig figs as well. You guys good? Okay. So, gang, did any of you print the notes? So you have no idea what's coming next. Okay. So we have about a... Oh, yeah.
Were they on your website?
Oh, poop. No. No. That's... I'm so sorry. I totally forgot to post them. I haven't updated our web... No. No, guys, I apologize. No, they weren't there. I mean, I can make excuses about just the crazy start to the year, but they weren't, and I'm sorry. I'll get it. I'll fix that. And I'll plan ahead for the next couple days. Okay, good there? All right, so guys, there's one more thing that there's a natural break in the material from chapter 3 that requires that we cover the next 2 ideas. Okay? So let's move forward, and we're going to wrap up these next 2 ideas, and then we'll be all set. So, gang, please do not try to write this information down. It will come back to you, but let's use the slides as talking points, and then we're going to engage in the calculations together. So, guys, last year we talked about something called empirical formulas, and you may remember that we talked about... I'll just write down a few. Do you remember this? And we said that these molecules, and C5H10O5, I threw up a couple extras, but we said that these molecules are all part of a class of compound that we call sugars. Sucrose, glucose, things like that. But guys, these are all sugars. And then we realized that they all have the same empirical formula. And if I told you that it was this, do you now remember what empirical formulas are? They're the simplified formulas for compounds. And then we had that weird aha moment where we said these are all called carbohydrates, and now we know why. Huh? Oh, yeah. There you go. But guys, the question then becomes, how do we calculate empirical formulas based upon data? And the answer is this. When we calculate empirical formulas, we always assume that we have a 100-gram sample, making our percentages equivalent to masses. Then we convert masses to moles. Then we find the whole number ratio by dividing by the smallest values. And you're going, okay, I kind of remember. But guys, let's do this. ethylene glycol, don't write this down, but we're going to do this together. Guys, ethylene glycol, actually, when you break it down and weigh the parts, is about 39% carbon, 10% hydrogen, and about 52% oxygen. What is its empirical formula? Now, guys, just so we can talk about this, do you know what ethylene glycol is? It's actually antifreeze. The thing that's really crazy about ethylene glycol is it's very sweet. You'll notice it's carbon, hydrogen, and oxygen, just like sugars, just like carbohydrates. It is very, very sweet, but it is also very, very poisonous. And so it's why a lot of dogs die. You accidentally spill antifreeze in your garage, your dog starts to taste it. It tastes like sugar, they lap it up, and then they don't make it. But anyway, ethylene glycol looks a lot like sugars, but it's not. So what is its empirical formula? Well, guys, we're going to calculate it. So join me on paper and let's do this. So I need these numbers, and I'm going to go to a blank screen. So let's do this together, and I think you'll remember this problem-solving process in just a minute. Okay, here we go. So guys, in order to solve these problems, what we do is this. So we take the percentages and we use them as masses. Do this with me. 38.7 grams of carbon, 9.7 grams of hydrogen, and then 51.6 grams of oxygen. And then, do you remember this? We do this. Is that coming back to you a little? And then we convert to moles. So 12.0 grams is 1 mole. 1.0 grams is 1 mole. And 16.0 grams is 1 mole. I'm realizing I'm going to be a lot happier if I have my calculator, which hasn't seen the light of day since May. All right, so 38.7. Uh-oh. Guys, my batteries are dead. Can you guys feed me numbers? 38.7 divided by 12? 3.23. And that's moles. This is math even I can do. And 51.6 divided by 16? 3.23. Okay, so now we have the mole ratios, but those are not whole number ratios. So we divide by the smallest number of moles, which is 3.23. Any number divided by itself is 1. Any number divided by itself is 1. This is approximately 3, and this is 1. I feel like I did something wrong. Is this all right? Am I okay? Okay, so then, guys, from that, we write the empirical formula, and we get CH3O, which you can see is 1 hydrogen proud of hydrocarbons, or of carbohydrates. Is that all coming back to you? Okay. Now, guys, last year, this was an end unto itself. Figure out the empirical formula. Because we're now going to take this a step further, and then we'll actually go in, what we're about to talk about here, we're going to do in lab. But let me explain to you the way that this works. So guys, CH3O is the empirical formula of ethylene glycol. Here's the question. Is that what ethylene glycol is? Maybe, but not necessarily. But the thing that we know for sure is if we can figure out what ethylene glycol is, it will be a multiple of this. Let that sink in. Does that make sense? In the same way that multiples of that sugars are always multiples of 1 to 2 to 1, yes? In the same way that sugars are multiples of 1 to 2 to 1, ethylene glycol has got to be a multiple of 1 to 3 to 1. So how do we then figure out what ethylene glycol actually is? And the answer is we play around with it in lab. So guys, what we are talking about now, come on. What we're talking about now is what is called a molecular formula. This you may want to write down. Guys, a molecular formula is the formula of a molecule as it actually exists. Oh boy. It's the structure or the formula for a molecule as it actually exists. Now guys, once you've got that down, stop taking notes and let's just talk about this. Please don't write this down, but here's the deal. Molecular formulas can actually be calculated from empirical formulas, but what you have to know is the molecular weight of the compound. Then in order to do that, here's what you do. You calculate the empirical mass, then you divide the molecular by the empirical, and that gives you a multiplier that you use to figure out the actual formula. So now you're going, wait, this makes absolutely no sense at all. Guys, check this out, and this is what we're going to do in lab. We could actually take ethylene glycol, and by reacting it with other stuff or burning it, we can work backwards and figure out how much it weighs. So, here's the data. Ethylene glycol actually has a mass of 62.1 grams per mole. We can now figure out what ethylene glycol is. Do this with me. So guys, look back in your notes. What is the empirical formula of ethylene glycol? CH3O. What does that weigh? Figure it out. What does that weigh? Carbon's 12, hydrogen's 1, oxygen's 16. What does it weigh? 31.0 grams per mole. So guys, that is what is called the empirical mass. But now look at what we know. We know the molecular mass of ethylene glycol. This will be one more minute. It's 62.1 grams per mole. So what we do is we go 62.1 grams per mole divided by 31 grams per mole. And what do we get? 2. Guys, that gives us the multiplier. So it turns out that ethylene glycol is actually double this. So it's C2H6O2. You get the idea? Okay. So guys, with that said, we need to talk about homework. So let's clear this, grab this, go over here. So guys, what you're going to see is this. The last slide in our notes will always be the homework. So guys, somewhere in your notes, or this will be posted by tonight, here's your homework. But guys, with that said, because we didn't get done with the day, we're going to pare this down. So the homework is 3, 5, 7, 14, 19, 25, 37, 45A, 49, 57, 63, and 79. These are all at the end of the chapter. So here's what we're going to do. Do number 3. Do number 5. Do number 7. You can do number 14. You can do number 19. You can do 25. Where do we go next? 37. You can do 37. You can do 45. You can stop at number 49. Don't do the last 3. So guys, when we get together on Monday, we will review these up to that point, and then we'll wrap up the day. So we're going to stop there. We're going to come back and we're going to move into lab next. Put this stuff away. Get out of here. If you're a few minutes late coming back to third period, take your time, take a break. Kaylee, sorry we kept you late. Guys, we'll see you in about 5 minutes. A little more. See you.